Hello children, let us understand arguments of a complex number. Suppose P is a point in complex plane. It is represented by ordered pair x, y. So the complex number z is equal to x plus iy. Line OP makes an angle theta with positive real axis. This angle theta is known as one of the arguments of complex number z. It is written as theta is equal to argz. Arg is short form of argument. Argument is a multi-valued function. If theta is an argument, then 2 and pi plus theta are other arguments, where n is integer. Suppose theta is first argument, then next argument will be 2 pi plus theta. Next will be 4 pi plus theta, and so on. First argument or principal argument is called as amplitude, such that theta lies between minus pi to plus pi. If theta lies between minus pi to plus pi, then argument theta will be called as amplitude. Now let us understand how to calculate principal argument. Suppose z is equal to x plus iy. We have to calculate principal argument theta. So first we have to calculate alpha such that tan alpha is equal to mod y by x. Alpha is an acute angle. Then we will calculate theta. Value of theta will depend on value of alpha and position of z, whether z is in first quadrant, second quadrant, third quadrant or fourth quadrant. So we will consider 4 cases. In case 1, z is in first quadrant. This angle is alpha. We know that theta is the angle that OP makes with positive real axis. So theta is equal to alpha. In case 2, z is in second quadrant. This angle is alpha. So theta is equal to pi minus alpha. In case 3, z is in third quadrant. This is alpha. So theta is equal to minus pi minus alpha. Negative, as we are measuring the angle in clockwise direction. Clockwise is supposed to be negative and anti-clockwise is supposed to be positive. Case 4. Z is in fourth quadrant. This is alpha. So theta is equal to minus alpha. Let us summarize the method to calculate theta we have just learned. First step, calculate alpha such that tan alpha is equal to mod y by x. Here alpha is acute angle. Second step, find out position of z, whether it is in first, second, third or fourth quadrant. If z is in first quadrant, theta is equal to alpha. If z is in second quadrant, theta is equal to pi minus alpha. If z is in third quadrant, theta is equal to minus in bracket pi minus alpha or alpha minus pi. If z is in fourth quadrant, theta is equal to minus alpha. Let us see one question based on calculation of principal argument. Find the modulus and argument of each of the following complex numbers. Part A. Suppose z is equal to 1 plus root 3i and that is equal to x plus iy. Mod z is equal to under root real part of a square plus imaginary part of a square. So that comes out to be equal to 2. To calculate the principal argument, first step is to calculate alpha such that tan alpha is equal to mod imaginary z upon real z and that is equal to mod root 3 upon 1. So that is equal to root 3. Tan alpha is equal to root 3. So alpha is equal to 60 degrees or pi by 3. Here real part and imaginary part both are positive. So z is in first quadrant. So theta is equal to alpha. Alpha we have calculated as pi by 3. So theta is equal to pi by 3. Part B. Suppose z is equal to minus 2 plus 2 root 3i and that is equal to x plus iy. Mod z is equal to under root real part of a square plus imaginary part of a square. So mod z is equal to 4. To calculate principal argument, again we will calculate alpha first such that tan alpha is equal to mod imaginary z upon real z. So that is equal to mod 2 root 3 upon minus 2. Mod is always positive. So that is equal to root 3. Tan alpha is equal to root 3. So alpha is equal to pi by 3. Here real part is negative and imaginary part is positive. So z is in second quadrant. So theta is equal to pi minus alpha. Alpha is equal to pi by 3. So theta is equal to 2 pi by 3. Part C, suppose z is equal to minus root 3 minus I, and that is equal to x plus iy. Mod z is equal to under root real part of a square plus imaginary part of a square. So mod z is equal to 2. Tan alpha is equal to mod imaginary z upon real z. That is equal to mod minus 1 upon minus root 3. Mod is always positive. So that is equal to 1 upon root 3. Tan alpha is equal to 1 by root 3. So alpha is equal to 30 degrees or pi by 6. Here real part is negative and imaginary part is also negative. So z is in third quadrant. So theta is equal to minus pi minus alpha. Alpha is pi by 6. So theta is equal to minus 5 pi by 6. Part D. Suppose z is equal to 2 root 3 minus 2i. So mod z is equal to under root real part of a square plus imaginary part of a square. So mod z is equal to 4. Tan alpha is equal to mod imaginary z upon real z, and that is equal to mod minus 2 upon 2 root 3. Mod is always positive, so that is equal to 1 upon root 3. Tan alpha is equal to 1 by root 3, so alpha is equal to pi by 6. Here real part is positive and imaginary part is negative, so z is in fourth quadrant. So theta is equal to minus alpha. Alpha is pi by 6, so theta is equal to minus pi by 6. Now let us see properties of arguments. First property, argument of z1, z2 is equal to argument of z1 plus argument of z2 plus 2n pi, where n is integer. If we talk only about principal arguments, we can say argument of z1, z2 is equal to argument of z1 plus argument of z2. Let us see its proof. Suppose z1 is equal to a1 plus ib1 and z2 is equal to a2 plus ib2. Argument of z1, let's say theta 1. So theta 1 is equal to tan inverse b1 upon a1. Argument of z2, let's say theta 2. So theta 2 is equal to tan inverse b2 upon a2. z1, z2 is equal to a1 plus ib1 into a2 plus ib2. This can be simplified as a1 a2 minus b1 b2 plus I into a1 b2 plus a2 b1. Argument of z1 z2 is equal to tan inverse a1 b2 plus a2 b1 upon a1 a2 minus b1 b2. This can be rewritten as b1 upon a1 plus b2 upon a2 upon 1 minus b1 upon a1 into b2 upon a2. b1 upon a1 is equal to tan theta 1 and b2 upon a2 is equal to tan theta 2. So this can be written as tan theta 1 plus tan theta 2 upon 1 minus tan theta 1 into tan theta 2. We know this is the expansion of tan theta 1 plus theta 2. So tan inverse tan theta 1 plus theta 2 is equal to theta 1 plus theta 2. Theta 1 is the argument of z1 and theta 2 is argument of z2. So we can say argument of z1 z2 is equal to argument of z1 plus argument of z2. Second property, argument of z1 by z2 is equal to argument of z1 minus argument of z2 plus 2n pi, where n is integer. We can prove this property as we have proved first property. Third property, argument of z to power n is equal to n times argument of z plus 2k pi, where n and k are integers. We can prove this property when we study the Myers theorem later in this chapter. Now let us see a couple of questions based on properties of arguments. First question, find argument z if z is equal to 3 plus 4i into 1 plus I into 1 plus root 3i upon 1 minus I into 4 minus 3i into 2i whole square. Argument of z is equal to argument of this whole. This is in the form argument of z to power n, which is equal to n times of argument z. So 2 will come here. Now this is in the form argument of z1 upon z2, which is equal to argument of z1 minus argument of z2. So we can write argument of numerator minus argument of denominator. Now these two are in the form argument of z1, z2, z3, which is equal to argument of z1 plus argument of z2 plus argument of z3. So we can write this as 2 into argument of 3 plus 4i plus argument of 1 plus I plus argument of 1 plus root 3i minus argument of 1 minus I plus argument of 4 minus 3i plus argument of 2i plus 2k pi. Now this can be simplified as argument of z is equal to 5 pi by 3 plus 2k pi. Here k is integer. Now we have to put the value of k such as argument of z lies between minus pi to plus pi. So we can choose k is equal to minus 1. So argument of z is equal to minus pi by 3. Second question, if argument of z lies between minus pi to minus pi by 2, find argument of z bar minus argument of minus z bar. This angle is minus pi and this angle is minus pi by 2. It is given that argument of z lies between minus pi to minus pi by 2. That means z lies in third quadrant. Let's say z is equal to minus x minus iy, so that its real and imaginary parts are negative. Z bar is equal to minus x plus iy. We just need to change the sign in between real and imaginary parts. Its real part is negative and imaginary part is positive. So z bar lies in second quadrant. Argument of z bar is equal to pi minus theta. Minus z bar is equal to x minus iy. Its real part is positive and imaginary part is negative. So minus z bar lies in fourth quadrant. So argument of minus z bar is equal to minus theta. Now we can say argument of z bar minus argument of minus z bar is equal to pi minus theta minus minus theta. So it is pi. In next video, we will see how we can represent complex numbers in various ways. If you have a question, you can ask me on my Discord server. If you have not subscribed my channel yet, please do so.